extraordinarily unusual object is currently streaking past our sun. The precise nature and purpose of this entity remains uncertain to us. Our ability to observe it has now ceased. However, we have maintained careful surveillance of this object for several months. We have assigned it the designation 3I Atlas, and we have classified it as an interstellar comet. Our knowledge base regarding this new arrival to our solar system is quite substantial. Within a mere 4-month period, the scientific community has produced nearly 100 research papers focused on 3I Atlas, and additional information exists beyond the official documentation. Certain aspects of this data can appear rather extraordinary. Therefore, today we will filter through the speculation and thoroughly examine everything essential to understand about 3I Atlas. Let us explore the trajectory of this interstellar visitor. Currently, 3I Atlas is executing its nearest approach to the Sun. This phase is referred to as perihelion. The maximum proximity occurs on October 29th, when the object will traverse within approximately 210 million kilometers of our star. However, in astronomical context, we generally employ a larger unit of measurement, the astronomical unit, or AU. A single AU represents the mean distance separating Earth and the Sun, which provides us with a relatable sense of proportion for the immensity of the solar system. Consequently, the perihelion of 3I Atlas takes place at 1.4 astronomical units from the Sun, indicating it does not actually achieve extreme closeness. Its position lies somewhere just within Mars's orbital path. Nevertheless, this represents the period of maximum activity for 3I Atlas. This marks the highest temperature it will experience, resulting in substantial quantities of material from the object's surface being expelled into space. This behavior is standard for a comet. We designate this mechanism as sublimation. This occurs when solid matter transforms directly into gaseous form because liquid states cannot exist in the vacuum of space. Sublimation produces a comet's characteristic appearance, featuring a diffuse halo and an extended tail. The halo consists of all the gas and dust being discharged from the object's solid surface. It is technically identified as the coma. The tail forms through solar wind. This term describes the continuous waves of radiation streaming from the Sun's surface. This wind forces back all the most lightweight particles of dust and gas from the coma and propels them away from the comet. It constitutes a magnificent demonstration of cosmic choreography. Regrettably, we are unable to witness this phenomenon occurring to 3I Atlas as it travels through its peak solar exposure because our vantage point is unfavorable. Whether by chance or by some other force, our observation of the perihelion is entirely obscured by the Sun's brilliant glare. Very well. We now understand 3I Atlas's current location and possess a reasonable comprehension of its activities. Therefore, while we await its re-emergence on the opposite side, this provides us an occasion to examine how it arrived here initially. This narrative is profoundly captivating. We have been monitoring 3I Atlas since July 2025. It was formally identified by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which actually comprises numerous telescopes distributed globally in locations including Hawaii, Chile, and South Africa. Their function is to observe the night sky and search for moving objects. This is precisely what they detected on the evening of July 1st. Simply another moving object. They therefore categorize it as a newly discovered asteroid and prepare to continue their work. Subsequently, they observe something peculiar about this particular one. Its velocity is excessive. All celestial bodies exist in perpetual motion. Every object within the solar system revolves around the Sun because we are all captured by its gravitational force. The fact that we maintain motion is what prevents us from descending into the gravitational well. The nearer you approach the Sun, the greater the velocity required to remain stable. However, if you begin to accelerate sufficiently, you actually begin to ascend from the well. If you attain a particular velocity, you escape entirely from the Sun's gravity and can travel outward into interstellar space, entering the emptiness that exists between stars. When astronomers calculated the velocity of this new asteroid, they experienced astonishment. This represented the fastest moving object ever detected within our solar system. Let us establish some comparative scale here. Planet Earth orbits the Sun at a velocity of 30 kilometers per second. That describes our motion. Our speed is considerable and our proximity to the Sun is relatively close, yet planets exist that are significantly nearer. Consider Mercury, positioned 0.4 astronomical units from the Sun's surface. It endures extreme heat, and to prevent falling into the gravitational well, Mercury must orbit at a velocity of approximately 48 kilometers per second. The new object discovered by Atlas was traveling at 58 kilometers per second. At that moment, it remained considerably distant, just inside Jupiter's orbit. That location is roughly 4.5 AU from the Sun. At that velocity, it was evident that this object would surge directly past the Sun and continue onward. We classify this as a hyperbolic trajectory, signifying that this entity had originated from the void of interstellar space and would return there after completing its extensive tour of our solar system. This is when the designation 3I Atlas was established. Third interstellar object, implying two predecessors existed. You likely recognize this one, Oumuamua, the first ever confirmed interstellar visitor. It also exhibited considerable peculiarity, though its strangeness manifested in an entirely different manner than Atlas's does, and we will explore that more thoroughly very shortly. We also possess a second interstellar object, the frequently overlooked middle sibling 2I Borisov, which actually displayed relatively normal characteristics. Beyond the fact of its interstellar origin, it essentially behaved like a conventional comet. Consequently, if anything, it was peculiarly unremarkable. Three significant distinctions separate 3I Atlas from its interstellar predecessors. The first is size. It is substantially larger. Oumuamua measured up to 400 meters across. Borisov reached a width of 1 kilometer, but 3I Atlas could extend up to 5.6 kilometers in width. The second is velocity. Atlas travels at approximately double the speed of Oumuamua and Borisov. The third is the direction from which the object arrived. This is the genuinely unusual aspect. Oumuamua entered from above, from the northern sky, which corresponds to the general direction of the solar system's motion. We all orbit the Sun, but the Sun itself also orbits around the Milky Way galaxy's center, dragging us along with it. As much as Oumuamua struck us, we also somewhat collided with it. 2I Borisov executed mostly the identical maneuver. It approached at more of a diagonal angle than directly head-on, but from the same general direction. However, 3I Atlas is not another frontal collision. This one resembles a T-bone impact, arriving on that lateral angle in nearly perfect alignment with all the planets. Our solar system resembles a disk of matter that all formed surrounding the Sun. Over time, all of that matter continued colliding with itself and coalescing into planets and moons and asteroids and other objects, but it all remained in a relatively flat disk configuration. We identify that disk as the plane of the ecliptic. Only a few objects deviate slightly from that plane. The most recognizable example would be Pluto. Its orbit is inclined by 17 degrees. Therefore, sometimes it exists slightly above the plane of the ecliptic and sometimes below. Understanding this is important so we can appreciate how precisely aligned 3I Atlas actually is. The interstellar object deviates only 3 degrees from that ecliptic plane. It struck our solar system in perfect alignment with the disk. Space exists in 3 dimensions, and that object could have originated from any direction. To have something impact us almost perfectly from the side represents a very significant coincidence. However, that leads us to an even more substantial question. From where did 3I Atlas originate? We know that it arrived from the direction of the galactic core. If we examine the Milky Way galaxy from this conventional overhead perspective, your location is here in this somewhat outer region of the galaxy, situated in a spiral arm. When you observe the Milky Way in the night sky, that represents the adjacent spiral arm. Regardless, 3I Atlas came from the direction of this luminous core in the center. It appears bright because it contains stars, and they are concentrated much more densely than those in our neighborhood. However, again, space exists in 3 dimensions. To truly comprehend where 3I Atlas originated, we must rotate the galaxy to a lateral view. Just like our solar system, most of the matter in the Milky Way is concentrated in a thin disk around the core. However, also like our solar system, certain objects exist above and below the thin disk. In the galaxy, we designate that region as the thick disk. The thick disk is considerably less populated, so you do not encounter nearly as many massive collisions and supernova explosions and black holes and similar phenomena. Therefore, objects in this region tend to exist undisturbed for extremely long durations. That is where astronomers believe 3I Atlas originated. This ancient region of space, which could render it as old as 7.6 billion years, nearly twice the age of our own planet. We will probably never succeed in tracing the journey of 3I Atlas completely back to its point of origin, but astronomers have recently succeeded in backtracking over 10 million years, and they have identified 93 stars that the object would have encountered during that period. What is profoundly fascinating is that throughout the course of that 10 million years, the nearest it would have approached any of those 93 other stars was a distance of 0.3 light-years. That equals 63,000 astronomical units. Currently, 3I Atlas is merely 1.4 AU from our own Sun. Let us now discuss in greater detail how 3I Atlas approached the Sun and what we discovered about it throughout the process. Although 3I Atlas was officially discovered on July 1st, it was actually detected for the first time on May 7, 2025. It appeared in images captured by the Transiting Exoplanet Survey Satellite, or TESS. This is an observatory that orbits Earth and peers deep into the galaxy, attempting to identify new planets in other star systems. For a duration of approximately 1 month, TESS happened to be observing in the direction of 3I Atlas. This provided us the opportunity to track the object as it moved through Jupiter's orbit. The first characteristic that astronomers sought to measure was the object's brightness and how it varied over time. This will inform us about the composition of this entity. We know that during the 1-month period that 3I Atlas was observed by TESS, it traveled approximately 1 AU toward the Sun. Consequently, we would anticipate it to become brighter during that time frame. Astronomers employ a term called flux to describe the perceived brightness of an object in space. Here is an illustration of how this functions. Consider how bright the Sun appears from your location at midday on a cloudless day. Now imagine you are transported to Mercury's surface. That identical Sun will suddenly appear substantially brighter, bright enough to incinerate you. The actual brightness of the Sun did not change, only your perception of it. That is flux. Therefore, astronomers had a hypothesis that the flux of 3I Atlas would increase by a factor of 1.5 between May and June. However, data from TESS revealed that the flux actually increased by a factor of 5. A massive increase in the quantity of light being reflected by this object occurred. This is how we know this is not an asteroid. It must be a comet that is beginning to form its coma of gas and dust, which is what is reflecting all of that excess light. Except, 2 peculiar aspects characterize this observation. One relates to the polarization of light. This is a challenging concept to explain, so we will oversimplify here. When light from the Sun strikes that cloud of gas and dust surrounding 3I Atlas, it will scatter in various directions. However, the direction that the light bounces is not random. It can reveal much about the material that the light is striking. If the light scatters laterally at a right angle or perpendicular, we call that positive polarization. If the light bounces directly back in a parallel direction, we call that negative polarization. Most objects in space exhibit mostly positive polarization, even interstellar objects. 2I Borisov was positive, but 3I Atlas is negative. Not only that, it possesses the most extreme negative polarization of any object ever discovered. That is remarkably unusual. It is just one of the numerous oddities about 3I Atlas that indicates not all solar systems are identical. What we consider normal here would be unusual elsewhere. What is normal in a different star system is considered unusual in our vicinity. The second surprising aspect about the coma of 3I Atlas was the fact that it existed at all. Remember, we are examining this period between May and June. 3I Atlas remains considerably distant beyond Jupiter's orbit. This is over 5 AU from the Sun. Conditions there are extremely cold. It is so cold that we typically do not detect comets at 5 AU because they typically have not begun to form their coma yet. They remain frozen solid. It is not usually until somewhere between 3 and 4 AU that the sublimation process truly initiates. This is because typical comets from our solar system are typically composed of water ice, which requires substantial energy to melt. However, as we continued to observe 3I Atlas and we began directing our most powerful telescopes directly at it, we learned that the coma was actually dominated by CO2 gas. It did contain some water vapor, but the ratio of CO2 was significantly higher at around 8:1. That is essentially the opposite or inverse of what we are accustomed to finding in comets. If you have ever observed dry ice, it is typically used to create a smoky effect for live performances. That is frozen CO2. It must be created and stored at incredibly cold temperatures. As soon as it is removed from the deep freeze, dry ice will instantly begin to sublimate, producing that signature cloud of gas. That is what 3I Atlas was doing far out there in space. That is why its coma formed so early, because CO2 ice melts at a significantly lower temperature than water ice. We have continued to observe 3I Atlas on its approach to the Sun. We have witnessed that ratio of CO2 and water begin to reverse. By late September, as it was passing through Mars's orbit at just over 1.5 AU, the object had actually begun to release a massive quantity of water vapor, approximately the equivalent of a fire hose running at full blast, which is actually more water than we would expect, even from a normal comet at this distance. We have never witnessed so much water vapor appear so abruptly. The same statement applies to metal in the coma of 3I Atlas. When it was observed during the summer, astronomers detected a small quantity of nickel in the surrounding cloud, but they did not detect any iron. Several points merit notation here. First, nickel and iron are fairly common in the universe because they are formed inside the core of a dying star. Then that star undergoes a supernova and expels these metals into the surrounding region of space where they get pulled in by new stars that are beginning to form their own planetary disk. The process then repeats. Because nickel and iron originate from the same source, they are typically found together in planets, moons, asteroids, and comets. When we observe abundant nickel but no iron, we wonder where the iron disappeared to. What process separated them? Second, it is unusual to see any metal at all sublimating from 3I Atlas given its distance to the Sun when this observation was made. It remains far beyond Mars in the region of the asteroid belt, which is still very cold, and the process of sublimation is driven by heat. Regarding CO2, we know that it does not require much heat to melt. However, when we are discussing metal, something else is occurring. Most likely the massive release of CO2 is dragging nickel atoms along with it. Nevertheless, that still does not account for the iron deficiency. Just like water vapor made a very sudden appearance in the coma of 3I Atlas, the same phenomenon eventually happened with iron. By late September, astronomers had started to detect iron for the first time in the coma. Then very quickly, the ratio of nickel to iron changed to a more normal combination of the two. Therefore, 3I Atlas is becoming more normal over time, but it is achieving this in a very strange manner. Let us now discuss tails. This is another area where 3I Atlas has behaved somewhat differently from your average comet. Primarily because the first time we observed a tail forming around 3I Atlas back in the summer, it was pointing in the wrong direction. This object initially formed a sun-facing tail. This is unusual because the tail is considered to be an effect of the solar wind interacting with the coma. The solar wind blows away from the sun. Therefore, we expect the tail to flow in that direction. In this case, it did not, which could be related to the early formation of the coma, which was due to the high CO2 concentration. Because the object began sublimating at a very long distance from the sun, it is possible that the solar wind simply was not strong enough yet to push the cloud of gas and dust away. What we observed was more of that cloud accumulating on the warm side of the object, the sun-facing side, before it encountered a strong enough wind to form a conventional tail, which is what 3I Atlas eventually did. By September, a short fan-shaped tail facing away from the sun had developed, which is fairly normal. Not all comets possess long streaking tails like what we are accustomed to seeing in illustrations. The length of the tail varies according to what the comet is composed of and its distance to the sun. For example, Hale-Bopp is quite famous for having a gigantic tail when it was observed in 1997. However, it was also very close to the sun at that time, approximately 0.9 AU, half of an AU closer than 3I Atlas will ever approach the sun. Naturally, it experienced more sublimation and solar wind, which shaped that tail. It is around this time that we actually obtain our closest possible observation of 3I Atlas. However, the view does not come from Earth. It comes from Mars. On October 3rd, the object passes within 0.19 AU of the planet Mars, the closest it will come to any planet in the solar system. This is fortunate for us because we have numerous cameras on and around the red planet, which means we were able to use them to image 3I Atlas. Here is a photograph taken by the Perseverance rover from Mars's surface. This is how the object would have appeared in the night sky. It is not an exceptional picture. This is not what the rover's camera was designed for. To capture this much light, the camera had to take 30-second-long exposures. Then several of those images were stacked on top of each other. What you end up with is more like a streak than a defined object. Here is another image of 3I Atlas taken by the European Space Agency's ExoMars probe, which orbits around Mars. We can see the object slightly more clearly now, but there is still insufficient resolution to distinguish between the bright coma and the surface of the object itself. To obtain that fine detail, we would need to take a photo with NASA's Mars Reconnaissance Orbiter, which has the most powerful telescope in the Mars system. Unfortunately, at the time we are making this video, that image has not been released, if it was even taken at all. Essentially, there has been a shutdown of the U.S. government, and people at NASA are not going to work until some political matters get resolved, which unfortunately could take some time. However, time is something that we have right now, because the sun will continue blocking our view of 3I Atlas until early December, at which point we will be able to study the effect that the sun had on the object. Although the closest that we will get is still 1.1 AU, that happens on December 19th. At this point, 3I Atlas will be well on its way out of the solar system. However, there is just one more close encounter still to come. On March 16, 2026, the object will fly within 0.36 AU of Jupiter. While we do not have nearly as many cameras around Jupiter as we do at Mars, we do have one. It is on a probe called Juno, which has spent the past decade observing the gas giant and its moons. It will have a chance to take one last image of 3I Atlas before it disappears. At this distance, the object will be cooling down. It will be less active, but it could be altered by its exposure to the sun. That will add an extra layer of understanding to these interstellar objects. It is entirely possible that many of these strange characteristics did not even originate from the place where the object was formed. It is just an accumulation of unusual material that it collected along the way. For now, we can only wonder, but more answers and probably more questions are soon to come.